I'm R. Prabha, Assistant Professor, the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on magnetic field intensity due to circular conductor for the course Electromagnetic Fields and Waves. So, in the last video, we have seen the calculation of magnetic field intensity due to straight conductor, and we have taken a straight conductor of length L, and it is placed at the origin, and at distant point P, we calculated the magnetic field using Biot-Savart's law, and we have found that magnetic flux density B due to straight conductor is mu naught divided by 4 pi 1 by r sine phi 1 plus sine phi 2. And in today's topic, we are going to discuss the calculation of magnetic field intensity for a circular conductor. So we are going to discuss this in a design thinking way. So we start from the first stage of design thinking, empathy. So in the empathy part, we have to find out the understanding of the foundation. So the Biot-Savart's law, which describes the magnetic field generated by static electric field, and it forms the foundation of current magnetic field intensity at any point in space due to current carrying conductor. So now the second stage is define stage. So in this we are going to learn the core concept of Biot-Savart's law. Its mathematical expression is dH is equal to ideal cross r vector divided by 4 pi r cube. Here r is the distance, r vector is the position vector, ideal is the current element, and its physical meaning, we have to identify each infinitesimal current element for the calculation of total magnetic field intensity using superposition theorem. And the various key variables here are I, current in amperes, dl is length element vector, r is the distance, and h is the magnetic field intensity. So now we have taken the geometry of the circular conductor, which is having the radius r, a, and the current carrying is I, and we have to analyze the magnetic field at various points in space for this structure. So we have to consider the on-axis point, which is along the perpendicular through center, and the center point is the maximum field intensity location. And next is the off-axis points, which require the integration in cylindrical coordinates. The symmetry of this circular geometry simplifies the mathematical integration process significantly. And this is about the ideate stage. And the prototype stage, we are moving into the field calculation at the center. We have to set up the geometry and the position circular loop radius A in xy plane, which is centered at the origin. And the current I flows in counterclockwise direction when viewed from positive z axis. And the second step, we have to apply the Biot-Savart's law to find out the magnetic field intensity. Here, every current element dl contributes the magnetic flux density dB perpendicular to both the dl, the length, and also the r. So due to circular symmetry, what happens is the horizontal components get cancelled, only the vertical components added up. So in the third step, we have to integrate the total current element contributions to find out the entire entire magnetic field intensity. So here the distance from each element to center equals the radius A, and angle remains 90 degree. So the final result is B is equal to mu naught I divided by 2A. So here A is the radius of the conductor, mu naught is permeability of free space, and I is the current through the conductor. So here the magnetic field at center points along axis perpendicular to the loop plane, magnitude inversely proportional to the radius. So axis field distribution is shown in the diagram. So for points along the axis at distance z from the center, general formula is magnetic flux density B is equal to mu naught Ia square divided by 2 multiplied by a squared plus z squared power 3 by 2. So from the formula we can understand that the magnetic field decreases when we move away from the loop along the axis. So there are various special cases in this. One is at z equal to 0 we get maximum field. At z infinity the field approaches to 0 because flux density B tends to 0. And at z is equal to A, the field at distance equal to the radius. So this is about on-axis field distribution. So now testing phase of design thinking. So in this case, we are going to see the applications of magnetic field for modern technology advancement. It is useful in various fields like electromagnetics and also the uh, introductive charging, MRI, etc. So far we have discussed about the fundamental principles of magnetic field from Weier's law, circular geometry and its analysis, and also we have seen the practical applications. So summary, in the summary part, we have first seen about the Weier's law and the previous topic recall, that is magnetic field intensity due to straight conductor. So next we came to calculation methods. First we have seen the loop configuration and the field at the center is calculated. On-axis field distribution is considered, and we have discussed the practical applications and finally key takeaways. Thank you.